can actually cause harmful effect on life and even change, alter its evolution. If I can have the next movie, please. What this movie is going to show you, what happens when we have coronal mass ejection, which is really a cloud of plasma, huge amount of material that is big enough to swallow the Earth, propagating at a speed millions of miles an hour or greater. It impinges on Earth's magnetosphere. Lucky for us, we have a magnetic shield. Most of these harmful radiations are deflected by this magnetosphere. Every once in a while, the field line of the sun and the field line of Earth's magnetosphere are aligned just right, and that's when some of these particles actually penetrate our atmosphere through the north and south poles, causing beautiful aurorae that we see, as well as harmful effects via geomagnetic storms and many other activities that goes on. So in some sense, life has flourished on this planet under the protective shield of this magnetosphere. The origins and fate of life are really intimately connected to the way Earth responds to solar variability. Recognizing this fact, this important fact, in 2001, NASA implemented a program called Living with a Star, whose goal it is to study this magnetic variable star and its impact on life and society. And Solar Dynamics Observatory is the very first mission of this program. I want to show you another steel chart called the impacts chart, just to give you a little bit more. This provides the reason for why do we study the sun in such exquisite detail. The top panel shows how the sun influences Earth's magnetosphere, ionosphere, mesosphere, atmospheres of other planets, to the very edge of the interstellar medium, as well as the basic plasma processes in the universe, as I said in the beginning. The lower half of the charts actually shows the impacts here on Earth. I think human society, with time, as it has become technologically advanced, become really vulnerable to solar variability. Solar variability affects astronauts working in space, space station, satellites in space, communication, navigation, just any number of events, including terrestrial weather. So the question is, we really need to understand solar variability. It's crucial to our modern way of life. In my way of thinking, it is a necessity, not a choice for a spacefaring nation like ours. What I'd like to show at this point is some of the ways we are attempting to share these fantastic observations. And what you have here is an application being developed for iPad, and this is just an example where you would be able to actually see some of these movies. Maybe, maybe not, but this is being developed and will be available soon for some of you to at least enjoy some of these spectacular movies. I think finally I want to end with one thought. I think in some ways SDO is being sort of compared as the Hubble of heliophysics. It's thought that it's going to revolutionize heliophysics much as Hubble Space Telescope has revolutionized astrophysics and cosmology, which is true. There is, however, a very key difference. While Hubble is designed to observe almost everything in the cosmos, SDO is designed to study in great detail only one thing, and that is our very own star. It is tailor-made for the study of sun stuff. Stay tuned for some really breakthrough science that have real relevance to life here on Earth. Will be coming through very soon. Thank you, and back to you, Dwayne.
Thank you. Ladies and gentlemen, before we open it up for questions, this is just the beginning, but yes, you guys are going to give an applause. Please give a round of applause for these folks up here and all of the teams that are involved in this incredible spacecraft. Okay, now you really get the feel of the spacecraft when it comes to the Q&A, and I'm going to try to write these questions down. They're coming in my earpiece here. And I'm going to ask Dean to start off with this. This is coming from Europe, and probably Lika may want to join in also. But how is SDO different from other solar observing spacecraft?
Well, SDO is like the culmination of a whole generation of putting observatories in space to study the sun. We've learned that we have to take things more rapidly. We have to be able to look at the whole sun, as well as zoom in to look at little parts of the sun. We need to look at the waves rippling across the whole surface of the sun to do the helioseismology that we want to do. To understand the magnetic field, one thing we didn't show today was that we're going to be able to not just make black and white grams of the magnetic field, but also show the strength and direction of the magnetic field. And so that's something we've never done before as fast as we're going to do it. And we have Eve as well. These are the result of people putting things in space, learning what had to be done, and figuring out a better way to do it.
I'll add in. I think Dean said most of it. I think it is the most comprehensive view of the sun. It is not that we are seeing the sun in the highest resolution, spatial. We've seen it with trace. But those were piecemeal observation, bits and pieces. When you see the whole sun, as you have seen today, it is showing connections that we have never seen before. And that is absolutely important. We are trying to understand the sun as a star, its connection, and ultimately its connection with our own planet, Earth. And I think SDO is going to contribute significantly to that endeavor like no other mission has done.
Okay, now I want you guys to really project on this one because I think this is the essence, and I think, Lika, you already touched on this, but this next question comes from the Pacific Coast. Why should the public care about NASA wanting to better understand our sun?
I'll take a crack at it. I think I've kind of said it. I mean, if you think about it, the sun controls our climate. It's spewing out solar wind at 1,000,000 miles an hour. It is the very source of space weather. I mean, it is 1,000 times bigger than any other object in the sky. My question is, if we don't study the sun, what should we study?
I'll offer a couple examples of technology that affects probably most people in the United States. One is GPS navigation systems. People use them on a very large solar storm. They've knocked out GPS navigation as far south as Florida. Another example is flying between countries. Sometimes they have to reroute planes flying from the United States to other countries, and they have to reroute them and spend millions of dollars to reroute and spend more airline gas or cancel flights because of solar storms. So there's some very practical examples of technology that we probably all experience.
Yeah, another example is power systems, power grids. A large solar storm will easily take out the power distribution in, say, northern Sweden. One of those happened a few years ago. One of the goals for SDO is to learn how to do forecasting for these large storms. If we're successful, it'll have big impact on the people whose lights otherwise would have gone out.
Okay, on a more basic note, virtually all the mass in the universe is plasma. That is to say, it's ionized and it's conducting and it's dominated by magnetic fields. In order to understand our universe, we really have to understand how turbulent plasmas behave, and the only place we can really study it in any detail is the sun. And if you want to take this closer to the Earth, the future of energy in the world is fusion reactors. And people who build fusion reactors look to the sun as the test of their models and theories. So we look to the sun to understand how we burn hydrogen to helium cleanly to produce energy.
Oh, well, I have a reason too. We work at NASA, or I work at NASA. NASA flies satellites, that's our job. When the sun is more active, satellites come out of orbit more quickly, and one of our goals is to be able to understand that aspect of satellites. We have astronauts in space. They can be harmed by radiation that is changed by solar activity. We want to understand and be able to predict that. So we have very practical applications